Uh, it's an absolute pleasure to welcome Iolo Jones, who's going to tell us about computing differential geometry. This is material he's been working on since for 3 or 4 years now, and it's one of the most exciting things that has happened from my perspective at the interface of geometry and probability in the last, I don't know, 10, 15 years. So I'm very happy that he gets to tell us about computing differential geometry. Take it away, Iolo.
Awesome, thank you. That's a lot to live up to, thank you. Yeah, it's great to be here and to see so many nice people, and also online. Thank you for joining. I should be able to hear you if you say anything online, so please jump in at every point when I'm going through this. So yeah, it's lovely to be able to present this. So as Philip said, this is something that I've been doing for a few years now, developing the theory and developing some applications. And what I'm going to present today is a new paper from a month ago or so now, which is introducing a sort of a new computational scheme. And the general outlook is about applying geometric methods that we have sort of classical mathematical. So I'm going to be talking about some computational methods for doing calculus and geometry and topology given data. So the sort of point cloud style data that we have here that often arises sort of experimentally, and we want to apply geometric tools for which we have a kind of rich classical theory, but a lot of challenges with trying to apply these methods. So I want to give basically an overview of what this is, where these methods fit in. So I think the way that I would think about it generally is about applying methods from calculus. So calculus in the classical sense is the sort of standard vector calculus that we have, where you might have a Euclidean space, and we have tools like the sort of gradient and the divergence and curl and these sorts of classical methods for talking about change and variability. So you could have a function like here, and then you can compute its gradient vector field, which measures the sort of the spatial flow as you go up the kind of the hills of the function. Taking this a step more generally, there's this sort of enormous classical field of Riemannian geometry, which is essentially taking the classical vector calculus methods and doing them in a geometric domain. So something here like a kind of curved surface, locally it still looks like a plane, and so we can sort of directly port the geometric tools, the calculus tools, from the Euclidean setting to the manifold setting, which is what we deal with in Riemannian geometry. So we can have something like this, which is the gradient vector field, and this is sort of a direct generalization of this idea where you have a function, it has a kind of spatial variability, and as you move around in the space, you can kind of plot this with these arrows that show how it all flows. Okay, so the big challenge practically is what happens when we only have data from the space. So the space is only implied by where your points are. So in this sort of environment here, which could be cells in spatial biology, it could be just arbitrary point clouds, arbitrary data, where you have, again, like a function on the data, it varies spatially, and the question is, how can we apply calculus-based methods to that sort of input? So there are some obvious challenges. One is that when we're in the sort of these continuous settings, we can define derivatives by taking limits. So you zoom in really closely around points, and that allows you to measure the variability kind of on the infinitesimal scale. Whereas if you only have finite points, you can't really do that. Like the points are separated, and so you can't just look arbitrarily closely. So we need some kind of non-locality that's going to be a proxy for this. So this is the kind of the practical challenge. And then I think I'm going to touch on this on the next slide. There's a really sort of key theoretical challenge as well, which is that the manifolds that we see in the middle, which are the kind of the standard geometric domain, there are very strict conditions that these have to meet in order for the geometry of Riemannian geometry to apply. So in practice, we have data that might not be a manifold, and so sort of developing a suitable theoretical framework is a big challenge. So I'm going to touch a bit more on that on the next slide about what that distinction is. But essentially, the point of this work and what I'm going to get onto today is showing how we can basically play the same game and get to the same. So yeah, the conclusion of this is going to get here, which is going to require kind of a theoretical jump to do it on non-manifolds and a practical jump to do it from data. So yeah, I want to talk about manifolds and what the relationship is here. So I'm sure lots of you have heard of the manifold hypothesis, which is a general assumption that we tend to make in machine learning and in data science. We assume that when we have data, when we have high dimensional data, that it will have some kind of low dimensional structure. So a classic example people give is like if you imagine taking an image of like the store, you can change certain things about it. You could change the color of the door or the color of the walls. There are certain sort of directions that you can go in, but you can't just like randomly change the pixel values and still get an image. So even though images are a very high dimensional space, the space of kind of natural images or like real images within it is a vastly lower dimensional thing because you can't just sort of pick arbitrary pixel values and get an image. So this is what people normally mean when people talk about the manifold hypothesis, which is you're in high dimensions, but there's some secret low dimensional structure that you don't know about. What is I think a kind of important psychological challenge here is that we call this the manifold hypothesis, but crucially, that doesn't mean that it's a manifold in the mathematical sense. So to kind of try and demonstrate this distinction, in maths or in Riemannian geometry, when we talk about manifolds, we mean basically a space that is perfectly homogeneous. So like everywhere you go, it always kind of looks the same. So here it's sort of, when you zoom in, it looks like a one-dimensional thing. And the crucial point is that everywhere it looks like that same one-dimensional thing. So in practice, when we say like data manifolds, if you study Riemannian geometry, this is the object that you study. It's something that is kind of smooth and homogeneous. The important distinction practically is if you have something like this. So now we have something that is still low dimensional, but it has these intersection points here, which mean that it's sort of heterogeneous. There are places where it looks like a line and there are places where it looks like a cross. And these are the sorts of things that manifolds are not allowed to have. So this kind of spatial heterogeneity is exactly the sort of distinction we want to make in practice, because real data can have these things, whereas classical manifolds can't. And similarly, if you have variable dimension like this, you can see it's kind of 2D on the left and 1D on the right. And this is also something that manifolds are not able to have. So separate from the dimensionality question, whether it's a manifold or not is really a statement about homogeneity, and that is unrelated to dimension. So you can have very high dimensional manifolds, like a million dimensional sphere. It's a manifold because it's homogeneous, but it's not low dimensional. So the big challenge quite practically is that we talk about data manifolds, so like images that have low dimensional structure, but what is meant by that is low dimensional. But in practice, these are often sort of heterogeneous in various ways. So the point of diffusion geometry, which I'm going to be introducing here, is about how we can take the classical methods that apply only to manifolds that are homogeneous like this, and make those same tools apply in the general setting of heterogeneous or spatially heterogeneous things, which is the thing that people mean when we say data manifold in practice, which is any of these would be considered data manifolds there because they're kind of structured, but only the classical theory only applies in this regime on the left. Okay, so I'm going to show a bit in detail about the classical theory, so the Euclidean geometry and then the Riemannian geometry, and then show how diffusion geometry is a sort of generalization of that. So the basic setup that I'm sure you'll have seen in different contexts before, where you have, say, a vector field on d-dimensional space, is that you can write it in this sort of formula. So it's like at every point you have a vector. These vectors are given by sort of coefficients, like functions fi. So if you're in 2D, you would have at each point two numbers that specify the direction of these vectors. And we can write them kind of like this. So this would be like grad x and grad y if you're in 2D. I'm going to show a demonstration of this on the next slide too. And this is the language that we can use for all of these things. So like differential equations and functions, vector fields, various different sort of techniques. When we move to Riemannian geometry, we're now on a manifold, and the point is basically that we can use the same kind of construction, but there's this abstraction step, which is essentially to generalize the pointwise dot product of vector fields. So if you imagine having two vector fields on the space, so at every point you have two vectors, you can evaluate their dot product, and that will give you a number at every point. So you can take two vector fields, you can evaluate the dot product everywhere, and that will give you a function because at every point in the space you have the dot product value.
A smooth function.
A smooth function, yeah. Yeah. So yeah, the regularity of this depends on the regularity of the, yeah. And a sort of important practical point that is going to be the computational trick that we're going to exploit here is that if you have a manifold that's embedded in a higher dimensional space, so like images embedded in, or sort of real images embedded in like all of potential images, but also like a circle embedded in the plane, you can make these intrinsic objects, so like the intrinsic functions, intrinsic vector fields, by taking ones that live in the ambient space and restricting them down to your manifold. So to visualize that, you can take, so the stuff on the left is like the Euclidean geometry in 2D, the stuff on the right is the manifold that's living in it. And we can take vector fields, so here we've got grad x and grad y, and we can basically project them down onto the manifold, and this will give us grad x and grad y, but as intrinsic things. So this is the sense in which the geometry of submanifolds is kind of inherited from the ambient one by projection or restriction. So you can take functions similarly and restrict them. And then we can also start doing things like multiplying functions with vector fields. So if you take this vector field, you multiply it by a function. So in the positive ones, it kind of speeds up. In the negative region, the arrows get reversed. We can do that for these things, and we can similarly restrict them to the manifold. So the point of this is to show what the two different sorts of geometry are, like the ambient things and the intrinsic things, and crucially the ways in which the intrinsic things can be obtained from ambient ones by kind of pulling them back. Does that make sense roughly? Okay. So now the jump, which is how can we reformulate this in a way that will be A, more general, and B, practically computable. So the step that we're going to notice is that this Riemannian metric, which is the thing that specifies all of the geometry via this dot product, we can perform this kind of expansion. So because it's bilinear, because it's a dot product, you can take these functions and you can factorize them out. So you can take x and y, which are these sums, and you get this double sum, and everything simplifies down. And the point of this formula is that that expression on the right, which is the metric of the gradients of things, has this sort of more general form. So if you have the Riemannian metric of grad something and grad something else, this is known as the carré-Duchamp, which is denoted by this gamma. And crucially, this is a more general thing. So this is something that you can define even when you don't have a manifold. So the point of diffusion geometry basically is to reconstruct everything using only this object. So Riemannian geometry is based on the metric. The metric you can expand in this kind of way. And by making this expansion, you can sort of plug this thing in here. And then this is something that's more general. And so if we can swap that out for something different, then we get like a different notion of geometry based on that. So I'm not going to really talk at all about the theory here today. This is a sort of a computational presentation. So the recipe for computation that we can infer from this is basically to do some kind of expansion like this. So you see here, I expanded it into the carré-Duchamp. So this is like the theoretical step, which is we want to find a formula for the geometric object involving just the gamma, the way that this thing has. And then given that, the practical step is that we're going to try and compute that gamma via a data-driven method. And there are several for this, and I'm going to talk about one today. And then you can plug that into your formula, and then that will give you basically a way of evaluating this. Does that make sense? So we want this thing, we write it in terms of things that look like that. And then if you've got terms that look like that, you can compute something like this and you can plug it in, and that will be your kind of recipe.
So what restrictions do you have in your G that you don't have in your gamma? You say that your gamma is more general.
So you can define gamma in more general settings. So if you have a manifold, you define gamma to be this, and that will give you Riemannian geometry. But if you have in general what's called a diffusion Markov triple, which is like this classical probability object, that will come with a gamma that can be more, you can define it on more general spaces.
So what properties do you still want to have about your gamma?
About the gamma. So you need it, essentially you need it to be positive semi-definite pointwise. So you need to, if you give it gamma of f, which should be like the pointwise norm squared of grad f. So that should be positive. And you need it to be bilinear in both arguments. So it should be a bilinear form that takes into functions. So xi, xj, gives you another function, and it's going to be positive semi-definite.
Do you need it to be symmetric as well?
Yes.
Symmetric.
Yes. And then if you want it to be a diffusion Markov triple, which has basically an analog of the Leibniz rule, then there's another assumption that is something else that you need. But we can maybe talk about that in more detail. Yeah. But it's quite weak. Yeah.
So when you take the Riemannian metric, these things are invariant with respect to like which chart you choose, right? And for this gamma, if I was to take an open set of say like a normal crossing singularity and then puncture it, would it still be like whatever chart or coordinate I choose for that punctured open set? Would it still have to be coordinate and like parameterization invariant?
So in general, it's only defined in a global sense, like a bilinear operator of functions. It isn't necessarily based on local representations, which you have on manifolds. So
can it be defined on
local ones?
Or
you could do. I mean, certainly if it came from a manifold, then it would have that. I think if you were to imagine, I mean, as a simple example, take manifolds, take a disjoint union of manifolds of different dimensions. So that space in its entirety is not a manifold, but locally it always is. You could define a metric by taking the metric of each of those and just sort of adding them all together, whatever. That would also admit local rep. So yeah, under certain assumptions, you can give it a local representation, but not necessarily always, because, for example, you can define these sometimes like on fractals, which maybe there's I don't know, maybe there's a way of sort of defining some locality thing there, but part of the abstraction is just to forget about local representations and think about them only as scalable objects. Okay. So I now want to talk about how this is sort of touching on why it's more general, but also how it relates to diffusion. So the point of diffusion is order to get a bit of generality, but it's also going to be a sort of computational trick that we're going to be exploiting. So let's talk about diffusion in more generality. So the standard heat diffusion, which I'm talking about, you may have seen this heat kernel expression, which exists in Euclidean space. So this basically measures the flow of heat after t time from a point. So at sort of time zero, it's just like a spike, and then it kind of diffuses outwards. And the key step that we're going to be exploiting is the fact that this Cauchy-Shank, so this pointwise dot product of grad f, grad h, we can write just involving diffusion via basically this covariance formula. So if you imagine the diffusion measures it's like a local bump function near a point, we're going to look at how f and h covary at that point, and that in the small t limit gives you an estimate of the gradient grad f dot grad h. So this thing maybe looks a little bit hard to parse, but this is a bit like the sort of the covariance of f, the covariance of h, weighted by the kernel, and we just shrink it down, and this measures the sort of pointwise relationship. So if you were just interested in the geometry, this would be a really weird way of writing the gamma, but the point is that this is something that we can use as a computational trick, as a way of gaining access to these gradients via the kernel PT. So to talk about how we can do that in a sort of data-driven setting, we can use an analog of this relationship. So first of all, let's pretend we've got n points, so we can evaluate for all sort of n squared pairs, we can get an n by n matrix of evaluating this kernel. We can then row normalize it into a Markov chain. So this is like a discrete diffusion process. So the thing I showed before was like the continuous diffusion in Rm. This is like the discrete analog of it. And then we're going to treat so a function here means a function on the data. So if you have n points, a function is like a vector in Rm if they're given by its evaluations everywhere. And we can just swap in the formula that we had before with this discrete version. So this is like doing the integral, but where we're now using this discrete object instead. So swap the sum for an integral, and that's this covariance thing from before. But the point is that here we can take a couple of functions and we can evaluate their carry Duchamp in this way. Yeah, does that make sense as an approach? So that, yeah, this is what we're going to be using throughout this process. This is just a way of computing it, and depending on the regime, you might have other ways of computing the gamma.
What happened to the t dependence? The 1/2t kill off all the t's that you see in the pointwise estimates, or is this whole thing depending on t?
This whole thing is depending on t, right? Yeah. So this will, when t gets smaller, this will, yeah. So that, yeah, there should be a superscript t or something. Yeah.
Well, more worried about the left side, I guess.
Yes. Yeah.
Is there, so regarding looking at the equivalent of the gradient, but are there higher order gradients?
Yes, I'm going to touch on that. Yes, there is. You can basically compose this operator with itself, and that will allow you to get at the Hessian and other second derivative stuff.
And these have the same property of generalizing across spaces.
Exactly. Yeah. So yeah. You can, but yeah, so the point is that everything boils down to just gamma, including like the Hessian. It's a second derivative, but you can write it as like gamma of stuff, and that will, yeah.
H.
H is another function, so f and h are a pair of functions, an arbitrary pair. So yeah.
Could you just go back to the previous slide?
Yeah.
You define your gamma as a covariance, but the only random thing is this x, and that's the input to the functions, but the functions themselves are not random.
No, exactly.
Okay.
Yeah. So f and h are functions, x is random, f of x is then random.
And p, so is that a probability? I mean,
He is a fixed point. Oh, capital P, sorry. This is fermentation. Do you mean this P? This is the point that
no, I meant the P. So you're not, that's not you're not taking that as probability distribution. That's just your heat kernel.
It is a probability distribution. This normalization thing makes it integrate to
one. Sure. Yeah. So it does integrate to one.
Mm-hmm.
So the two equalities there, you're taking an expectation over the x and y in your so P is the distribution that you take that expectation over.
Yeah, exactly. Cool. And in fact, this is exciting as well, because something that Jacob and I are working on is to use like a denoising objective to train a neural network to estimate this. And that's very explicitly using the fact that it's a probability distribution, so you can sample from it and use this as in training. Okay, so I'm now going to show how we can do that thing on the first slide, which is visualizing the gradient of a function given just samples of points. So putting all of these pieces together, if you have a function, its gradient is vector fields. So the theoretical bit, which is finding a recipe involving gamma, we can do in this way. So if grad f is a vector field. We want to visualize that as arrows. The way we can visualize it is having it act on the coordinates. So this is like taking the directional derivative along grad f. So if you've got your n coordinates, this looks like grad f of x1, grad f of x2, all the way up to n. We can do this via this pointwise dot product with the metric. That's sort of the definition of grad f of something. And then this just involves the gamma. So the object that we want, this collection of arrows, it has this formula involving only the gamma. And we can then compute it practically by plugging in this recipe for estimating gamma from data. So gamma of f with x1 up to gamma of f with xt. And that arrives at this thing. So what I'm showing here are on the left, the theoretical ones. So this is in Euclidean space, the gradient, on the manifold, the gradient. And now here, this is kind of computed exactly. This is now our estimate. So we have a sample of f, a sample of points from M. We evaluate f on those points. And then we can plug in this formula and we get a gradient vector field estimating this one. But the really crucial point is that even when you have something that isn't a manifold, so the heterogeneity that you see on the right, there's kind of a bit of 2D bit, there's that kind of intersection point on the right. All of these things make it fail to be a manifold, but you can clearly see there's like a sensible notion of gradient that this method is still getting. So we're kind of checking that in the manifold case it's still okay, but in the heterogeneous case, which is the kind of practically really important one, we are still getting something good. Okay, so that was basically the overview of the method. So just to recap, you write something involving gamma, you can compute gamma with the kernel, you plug it in, and then you just sort of get all of these things come out. So that's what am I going to talk about now? The challenge here is most of the interesting information that you want to have is encoded through differential operators. So this is like the gradient that maps a function to grad f, or if you're more familiar with geometry, you might have differential forms and you can have the exterior derivative that goes between them. You can have different Laplacians, the Hodge Laplacian, all of these objects, and the Hessian, various things like this. So the challenge is, given this representation, how can we find operators that map between them? So the sort of basic recipe we're going to have is to construct bases or spanning sets for the spaces that we want. So like the space of vector fields, the space of forms. And we're going to use these in order to represent linear operators between them, basically as matrices. So you pick some set that represents functions, you pick some set that represents vector fields, and then the derivative is now a matrix that maps from vectors in one to vectors in the other. And the point is that this is all going to be kind of simple linear algebra. So because these are all like linear differential operators, we're going to be able to access linear tools, which is nice conceptually because they're quite simple, but also practically it's amazing because you can use really optimized software that deals with linear stuff. So I'm just going to touch briefly first on what the spaces are. So when I say we want to represent the space of vector fields, that involves picking either a basis or a spanning set. So I'm going to show what the spanning set is that we're going to use, and that's going to be the kind of the base for these representations. So if you have data that's embedded in R to the D, then given an arbitrary vector field, you can represent it using this kind of expansion. So if you've got your d coordinate functions, so grad x1 up to grad xt, these are like the kind of principal coordinate things. And if we want to represent general vector fields, we want to be able to multiply these by functions in order to get more interesting combinations. And so the trick that we're going to use is to pick some choice of coefficient functions phi I, and then take sums of these. So if you take enough coefficient functions, you're going to be able to represent as many vector fields as you want. So here we're taking n1 of these, where this is some parameter that we pick, and then your d ambient coordinates. And so by taking these kinds of sums, you're going to be able to represent some more complicated things. So the choice is kind of arbitrary. You can pick whatever functions you like, but A natural choice that we're going to do is to take the smoothest ones that we can. And these are going to be eigenfunctions of the Markov chain. So I don't know how familiar you are with like sort of diffusion maps and manifold learning based methods. These are all roughly speaking based on like how you find nice smooth functions over your data. And we're basically going to use those methods to get a function basis, and we can plug that in as a way of getting these representations. So picking these, the space of vector fields is like R to the n1d, because you have your coefficients of these where you've got n1 choices of that and d choices of that.
So I understand how you construct this Markov chain by calculating your p and then normalizing. But is there any important property about this Markov chain? Like, for example, if you run this Markov chain, do you sample more data from your manifold or from your, not manifold?
Yeah. So there's the important theoretical connection is that the eigenfunctions of this estimate eigenfunctions of the Laplacian when you're on a manifold. So that's the kind of the motivating idea.
When you're on a manifold.
When you're on a manifold, and it's unknown in general.
Okay, so again, it's sort of a natural generalization, and then we just see what we get.
Exactly. That's the vibe with all of this. Yeah. I'm working on those generalizations with various people, but it's like it's hard. Yeah. So to kind of illustrate this, so these are the choice of functions on the left. So these are the first 4 Laplacian eigenfunctions we get, or Markov chain eigenfunctions. So the first one is just a constant, and it equals 1 everywhere. And as we start going down, they start oscillating more. So the second one kind of varies left to right. The third one has this kind of double dip. The fourth one goes up and down kind of vertically. And so this is our kind of function basis. And then we're going to start combining this with vector fields in order to span them. So in the top row, you can see grad x and grad y. So these are flowing left to right and flowing down to up. And as we start multiplying these by the functions in the column on the left, we can build up more and more complex and interesting vector fields that we're going to use as our basis. So you can see this one kind of goes back and forth. That one goes like, if you track the color on the left, so red is positive, blue is negative. So in the blue region, the arrows are reversed relative to just what grad x and grad y were. And so, yeah, if we start taking enough of these, we're going to end up being able to represent whatever vector field that we want. And then similarly, this is in 3D, so this is a little bit harder to see just in this screen, but here we've got grad x going like this, grad y is going in, grad z is going up, and in exactly the same way, we take a function, you start multiplying it, and you start getting more interesting stuff. Okay, so I've touched already on visualizing vector fields. The point of this slide is going to be to demonstrate that the computations that you get in the spaces are easy and they're linear. So like I was saying before, to do this visualization, you want to have the vector field x act on your coordinates. So you want to evaluate this vector. If we let x now be represented in our basis, so x is this xij coefficients array, then we can plug everything in order to expand this. So I'm sort of not asking you to read these lines, but just to show that we have the object on the left that we want, which is x acting on a coordinate, and the thing that we get at the end ends up just being like a big tensor contraction over x and u, which are the coefficient functions, and x and gamma. And so you can kind of pre-compute these matrices and tensors, and then basically everything here is like one line of code. It's like a NumPy Einstein summation where you just write down the formula at the bottom that you want, and you just contract everything together, and it's really easy. Yeah, and then similarly with the Riemannian metric, again, we have some kind of tensor of interest, which is the metric of phi grad xj and phi k grad xl. We can write this in this kind of form. You expand this all out, and again, we just get some kind of big matrix contraction together. So visually looking at what we have here, so here x, this is now something that we've represented in our basis. So this is a linear combination of those basic elements. We can evaluate its pointwise norm. So this is like because G is a pointwise inner product, so G of XX is like the norm of X squared. So the square root of that is the pointwise norm of X. If we evaluate it to the point, we get like a sort of heat map of the support of X. And then more interestingly, if you want to do the inner product, that involves sort of measuring the local alignment or correlation. So you can see on the right, they're both going uphill. So you have a positive inner product. But on the left, X is coming back down and Y is going up. And so when you take the dot product, you get something negative. Okay, I'm going to skip this, but this is about forms. So that was introducing what these spaces are. Like I was saying, this key question is how can you represent an operator? So if you've written down this choice of basis, how can I represent like grad as a matrix that takes in a function and gives you out a vector field? So there are some challenges here. We want to represent them involving the spaces, but like a priori, you don't know what that is. And the representation that is appropriate obviously depends on the choice of basis that you made. So because we're looking for a matrix, writing a matrix in a basis involves knowing the basis. And because we just made up the basis, it sort of isn't obvious what that is going to be. So the solution we're going to use is this standard trick in numerical analysis called the Erlangen method. And that is basically to exploit the inner product structure that we have. So to kind of walk through it. Let's look at this example here. So we have grad f. We want to express it in this form. So we want to given an f. We want to find the xi xj that mean that this expansion is equal to grad f or kind of close to it. The trick is that we're going to basically hit grad f with inner products with all of the other things in our basis. So if you have phi I prime grad x j prime, so that's like an arbitrary basis element, we can plugging in the fact that grad f is this, we get this expression here. So the xi factor out, and we get this formula here by linearity. And the thing that we notice is that if we let x on the left be this what's called the weak formulation, so this is this inner product expression. So for each, it's length n1d, because for each of the basis elements you get a number here, so we get a vector. And then the thing on the right is the coefficients that we want multiplied by the Rham matrix. And the Rham matrix is the matrix that encodes all of the potential inner product pairs that you have. So in this case, the thing on the left is a vector in R to the n1d, and the thing on the right, or the Rham matrix, is an n1d by n1d matrix. So this is going to be something that we can solve. So the thing on the left, if we call this grad f weak, this is a nice expression that we can involve by plugging in all of these things. We get something involving the gamma. Similarly, that involves the Carré-Duchamp. So we can compute all of these bits, and then we can solve this for x. So we end up with a matrix vector product. The vector here is g times x. And then if you invert g, you can solve for x. And in this sense, you're like, the thing on the left and the thing on the right both depend on your basis choice. And so when you solve this, you kind of cancel them out somehow, and you end up with something that like is the basis specific representation of, in this case, grad. Okay. Is that okay? Yeah.
So, but you still have to choose your original choice of bases, right? To solve this.
Exactly. Okay. Yeah. And this is kind of like a inductive bias. Like it depends on the choice of xi that you use and the choice of phi I. And you can pick them basically optimally for each. So yeah, using these eigenfunctions is like picking smooth functions, which is like generally quite a sensible thing to do. But maybe if you had other functions that arise from the application, then you could use them. Mm-hmm.
So you mentioned inductive bias, and this was sort of a question that I was wondering about for a while now. So you're talking about doing this for points, right? So you said earlier that your story was that you've got these things that work for manifolds, and you just generalize it and you see what happens.
Yeah.
But you could also say, okay, well, these points are a sample from a distribution. So you could have done this all on continuous distributions from the start, right?
Yeah, right.
So do you have any convergence results of what happens when you gain an infinite number of samples? Like, does the inductive bias matter? It shouldn't matter.
It shouldn't matter, no.
Yeah.
No. Yes, there are a couple of questions. So one is, if you start with the gamma that you know kind of a priori and you're in the continuous domain, then you can define the geometry, and that's sort of what the theory of diffusion geometry is doing. The second question is, like, if you were to use this kernel-based covariance thing and take its limit as t goes to 0, and you're in the continuous domain, does that convert? Like, what does that converge to? And this is something I'm working on presently. It's sort of interesting. It's not very trivial. For example, like the instance I gave where you have manifolds of different dimension, you will, if you were to do this construction, you would converge to the metric on each one, but it would be weighted differently based on the dimensions. So the kernel choice that you make to some degree is going to determine the geometry that you get in the end. And it's not trivial exactly what that relationship is. Even in the manifold case, there's like a dimension-specific weighting. The challenge is like when you have these intersection points, and then it can get complicated. So there are notions of in kind of metric measure space theory, that there is work on like how you explicitly construct more general geometries. Like the Chiga energy, there's a lot of work here that kind of gets it. So under certain conditions, this will converge to that. But the whole thing is generally quite complicated. So
that really helps, actually. So if your data actually does lie on a manifold, then you can take the limit of this t to 0.
Yeah.
If it doesn't lie on a manifold, then what the geometry that you get depends on this choice of your heat kernel.
Exactly. Yeah.
Yeah. Okay.
I mean, even if it does lie on a manifold, it will depend on the choice of the heat kernel. But if you use like the heat kernel, then it will get the correct thing.
Yeah.
But for example, I mean, say if you had a.
But one thing it doesn't depend on is the choice of your bases.
Right. Exactly.
Yeah.
Yeah.
Okay.
I mean, practically it does because it's finite and stuff.
Yeah.
And even if you're on a manifold, the choice of kernel could get you other things. So say, I don't know, say if you wanted to take a quotient space, you could use a kernel that somehow like sees the quotient. Like say if you took a sphere and then you made the kernel be like local here, but also you were close to like points on the opposite side. So the kernel would basically give you like the RP2 because you've identified like opposite points across here. And so you're using the RP2 kernel on the sphere. And so what it sees is like the geometry of RP2 in that sense. So yeah. Does that make sense? Close enough.
The stuff that I really needed to know, yes.
Was the first bit. Okay, perfect. Okay. I think that's the end of the sort of like conceptual discussion. I think the rest of this is basically like figures that demonstrate that you get sensible stuff from this. So this is the example we've been using all the way, which is the gradient. So on the left we have functions, on the right we have gradient vector fields that we evaluate. By now we're computing the gradient as an operator, so it's a matrix. You take a function, you apply the matrix, that gives you a vector field, and that's the thing that you see. So the bottom one is a manifold, so it's a kind of Swiss roll, so it's like a rectangle wrapped up. And the top right is not a manifold, again, because it has this sort of interesting heterogeneity. So you have these splitting off points, you have kind of 2D bits and 1D bits that make it non-manifold, but it's still low dimensional, and we can still kind of apply this thing, and you get that. Okay, so now we can look at divergence. So in the kind of Euclidean sense, this measures like expansion and contraction along a vector field. So here, if we look in the middle, you can see X is kind of growing, and that corresponds to the divergence being positive because it's expanding space. Similarly, where X is contracting, we get these blue bits where the flow of X is kind of coming in really quickly, and so space is contracting, and you have a negative divergence there. And again, this is like a non-manifold example on the top to give a manifold example at the bottom. Similarly, you can see X is kind of flowing from the top to the bottom, so it expands space on the top of the torus, and you have positive, and on the bottom it's negative. I think all of the examples I'm going to show are generally going to be manifolds in the 3D case. That isn't because this only works on manifolds in 3D, it's just because it's really hard to visualize when these are static images, it's really hard to see 3D structure when it's not just like a ball. So the 3D ones are all going to be quite boring, but trust me, it still is okay. Okay. So I skipped the bit about forms earlier. If you know what these are, there's this notion of one forms, which are like vector fields, basically the things on the left. Two forms are, they can encode a load of stuff, but the key thing here is that you can use them to encode vorticity. So if you have a one form, its gradient, so d alpha is a two form, and this measures how rotational the one form is. So on the left, we've got, and by the way, if you know about curl in the Euclidean sense, then this is just the curl. So if you're in 3D, the curl you can obtain from the derivative two form, but the general setting is that vorticity is measured by d alpha, which is this two form thing. So if we were in 2D like this, alpha, when it's, let me see, anti-clockwise, then we get this kind of red sign vorticity. When it's clockwise, it goes the other way. So you can see it's measuring like where and how much it's rotational, but also in what direction it rotates. And to give a 3D example here, this is like an anti-clockwise vortex. Well, no, it's a vortex like this. So when you see it from above, it looks anti-clockwise. But if you imagine like looking at it from underneath, it would look clockwise. And so these things are like red on one side and blue on the other. And that kind of measures the angle of the rotation as depending on which side you're looking at it from. Okay, so a similar kind of trick that we can get from this is to split apart vector fields. So I want to start actually on the bottom because this is more interesting. So this is the Hodge decomposition or the Helmholtz decomposition, or various names for these things. So you can take in this case, a one form that you can sort of pretend it's vector field. This will have rotational components, which are divergence free or curl only, or depending on what name you use, and parts that are rotational only. So this bit in the middle is the gradient of a function, and the bit on the right is the rotational bit. And so every vector field you can uniquely split up in this way into the gradient of something and then a part that is just rotating. And there's a sort of, this generalizes to forms of different degree, but looking at functions, the generalization of this is you can have a harmonic bit of a function which is locally constant. So here f like flows left to right. The bit on the middle is picking out the average over each component. And then you can separate that from the other part, which is like the variability only bit. Okay. I'm glad to have been able to get something moving into this. So here we can solve spatial PDEs with these kind of methods. So this is the heat equation on the left, the wave equation on the right. These are PDEs that you can write using the Laplacian, and then using kind of standard tricks, you can just evaluate their evolution over time. So on the left, we start with a density that just kind of diffuses. And then on the right, we have a kind of wavefront moving around, and you can see it kind of bounces off the edge. And I guess the important point to see in this is that it's all like a data-driven thing. So at no point did we specify like this is where the boundaries are. It's just something that is evolving according to the geometry that we've learned, and it knows that you should sort of reflect, and then you see it kind of wraps around here and it meets, and it has a wave, and then it kind of dissipates back out again. In a way that is like relative just to the spatial geometry that is inferred from the curve. Okay, this is a similar example. It's within the theme of like solving spatial PDEs. Before that was involving the Laplacian. We can also do it with a vector field. So I can take on the left this kind of rotational flow, and then on the right, I can just propagate that flow forwards by evaluating the coordinates under that flow, and that will show over time how these points would evolve as they were to follow like the integral curves or the flow lines of that vector field. Yeah.
Just an example, just a question about that example.
Uh-huh.
So so far in the whole framework, you said that you find that every point has a value.
Uh-huh.
And then from that, you get all this geometry and so in this example, where do you get the flow from? Does every point just have a value, and then this is the vector field that you get from?
Do you mean where do I get this from?
Yes.
Oh, here I'm treating it as given, so this could be from anything.
Okay, so the data that you give is now not a point and a value, but it's a point and a vector.
Yes, exactly.
And then you derive the entire flow, continuous flow
from
from
there.
that.
Yeah.
Okay.
So yeah. I think like Riemannian geometry, even though it's called geometry, is basically like calculus methods. So all of these things are really like they're operators that act on stuff in some way. So pretty much everything that we have here, the geometry tells you what the operator is, but then if you want to actually use it, you have to take in like a function and then you differentiate it, or you take in a vector field and then you flow along it, or you decompose it, or whatever. Yeah.
Previously, you were able to pre-compute our gamma, right? As a combined matrix between the points. But if the points are mean here, we get our value for gamma after a few time steps.
Yeah, really good question. So for this particular trick, there's no reevaluation of it. So this is saying the way you can interpret this is saying that at time 0, you have like x and y coordinates. These are functions, and then you can evolve those functions forwards. So you're in a sense, the point isn't actually moving. It's just that the x coordinate and y coordinate functions are evolving in the way that, like in this example, I start with a function and I propagate that function, but the points are fixed. Here we're just doing that, but on the x and y coordinate functions. So we're not actually reevaluating gamma ever.
Okay.
Yeah. Although you can see I've only run this for a short time. That's because over longer times it would get more unstable. So I think if you actually wanted to use it, you would want to do some short time integration and then reevaluate, and then yeah, do that kind of trick. Okay. Okay, so what I just said to you was about assuming that you take like a given input function. There are a bunch of ways in which you can use these tools for a kind of static analysis where you only have the points and you want to, for example, know stuff about the shape of them, like their curvature or their topology. So this is describing the way in which you can apply these to do topological data analysis. So here we're taking data that has holes in it. So on the kind of left and the right and the bottom, and there's this operator called the Hodge Laplacian that acts on one forms, and if you look at forms in its kernel, these basically characterize the topology of the space. So in this case, we on the Hodge Laplacian as a matrix, you can diagonalize that matrix, and the first 3 eigenvectors of it are these 3 things, and these are quantifying the fact that there are these different holes in the space. And then taking it a step further, we can find circular coordinates for these. So these are like an angle from sort of 0 to 360 that measures like how far around each of these you are. Okay, I think I'm going to skip the rest of the things because we're nearly at the end. I just want to briefly show this slide, which shows that it's quite quick to compute. So this is comparing against RIPSA, which is like the standard way of evaluating persistent homology, which is the way that people do topological data analysis. And you can see basically the scaling is much better. So partly that the curves are lower, meaning that they're quicker, but also that the angles, the slopes of the curves are a lot lower, meaning that you can kind of scale it to much bigger data and it's going to be a lot quicker. So for example, going to like 10,000 points here takes 1 second with these methods, whereas the scaling properties that we have with persistent homology is a lot quicker. Yeah, I'm going to leave these last couple of bits, but yeah, that's the end. Thank you for listening and for your many questions. I feel like people asked hundreds of questions throughout, so don't worry if you don't have any spare ones there. Are there any ones online if anybody has any that they want to jump in with?